Good morning everyone, welcome to the last lecture, the lecture 10 of this course Nonlinear and Adaptive Control. In the last class we were talking about the fourth method, that is the projection based modification, which was a robust adaptive control method to constrain the parameter estimates to lie within convex bounded region. So, we had done some preliminaries to start with. So, now we will continue and see how using those preliminaries we can actually construct projection based adaptive modification laws, and then further use them to prove that the estimates always stay bounded and that Lyapunov stability is preserved. Okay, so, the basic idea of this projection based modification. So, this is another robust adaptive term that we will use. So, the basic idea is to construct a convex set. So, just for convenience I am constructing a circle here and considering this to be a 2-dimensional space, but it could be an n-dimensional space and you could construct a convex set. And what we have assumed here is that this convex set is known, which means that we have certain information about the unknown parameter say theta. So, we know that the unknown parameter theta lies within this convex set and we are trying to estimate this theta. So, we design update laws for theta and we denote them by theta hat, and because we know this convex region in which this unknown parameter lies, we want to start our updation process from within this convex set. And so, we choose at initial time say t equal to 0, we choose theta hat of 0 to be within this convex set in which the unknown parameter theta lies. Okay. So, then as I mentioned in the previous class, theta hat will update based on the adaptation law derived using Lyapunov analysis for the unmodified case. So, let us say that that law was theta hat dot equals say y. Okay. So, this y in the MREC case was, if I remember correctly, it was gamma B transpose P E x transpose. So, this was the adaptive law for k x hat, right. So, suppose that is denoted by y, okay, and so theta hat is getting updated based on this update law, and it is moving inside this convex set, okay, in a continuous way. And then as long as it is within the convex set, there is no problem, we continue to use theta hat dot equal to y, but when it tries to come at the boundary, when it is at the boundary and it is trying to point outside, that is where we want to project it back into this convex set. Okay. So, so how do we detect that this theta hat is on the boundary and is trying to go outside? So, for that what we do is we look at the let's look at the let's look at this more clearly. So, let us say this is the boundary of the convex set and the theta hat is trying to move out. So, this y denotes the derivative of theta hat at this point on the boundary. So, let us say this this is at the boundary and we calculate the derivative, and based on what theta hat dot law that we had prescribed, we find that it is pointing outside of this convex set. Okay. So, then just to mathematically determine that it is pointing outside, we construct a gradient vector at this point, and we take the dot product. So, we take the dot product of we project this vector onto this gradient vector, and we see if the dot product is positive or negative. And if the dot product comes out to be positive, it means that the vector y is pointing outside of the convex set, and if the dot product of y and this gradient of f comes out to be less than equal to 0, then it is either pointing along the tangent, or it is trying to point it is pointing inside, which means that at the next instant it will either be on the boundary of the convex set, or it will move inside. So, yeah, so we start inside the convex set, and as long as so this is as long as we continue to use this update law till the estimate theta hat of t is within the convex set. So, we do not do any modification to it. Okay. And then on the boundary, of the convex set, there are two cases. One is when the dot product, which is in matrix vector notation we write as y transpose del f theta hat, is less than equal to 0, which means the direction of y is either tangential to this curve, or it is pointing inside of this closed curve. Then we still do not modify this update law. So, we use theta hat dot equals y, right. We continue to use this update law, because we are sure that in the next instant it will not go out. So, the second case is when y transpose del f of theta hat is greater than 0. So, this is the case where we know that the estimate is trying to move outside of this closed convex region, and that is when we want to project it back. So, how do we project it back? We do not stop the updation, rather we take the projection of this y along the tangential plane. So, we construct a tangent at this point, okay, and then we take the projection of y on this tangent vector, and this vector that we get is what we call as, say, the let's call this as tangent at theta hat comma y. So, it is a function of theta hat and the derivative at theta hat derivative y. So, how do we find this tangential vector? So, we know that this vector is basically given by, you can use the law of vector addition here, and it is it's basically this vector y minus this vector which will give you the tangential vector. So this is some multiple, some factor of this gradient. So let's call that factor as alpha times gradient of f of theta hat. Okay, so we can say that this tangent vector is y minus alpha gradient of f of theta hat. So now of course we need to know what this alpha is. So we can use the fact that this tangential vector and the gradient vector are orthogonal to each other. That is, this if we take the dot product of this tangential vector with this gradient vector, we will get 0, and then we substitute for this expression for the tangential vector. Okay, and alpha is some constant. Okay, so then what we get is y transpose minus alpha del f transpose f equal to 0, which will give us y transpose del f is alpha del f transpose del f, which will give us alpha as y transpose del f over del f transpose del f, which is same as y transpose del f over del f square. Okay. So we can say that the tangential vector at the point theta hat, which is on the boundary, is given by y minus alpha y, which is alpha gradient del f, which is given by y transpose f over gradient of f square times gradient of f. So this can also be written as y minus, so we can, since this is a scalar, we can always take the transpose of this and we get and this is also so y transpose del f is in fact we can take the transpose of this, and what we get is del f transpose times y, right. Okay, so this can be moved to the other side, since this entire term is a scalar, and then we take the transpose of that. Okay, so what have we achieved here? So we have actually the projection modification adaptive law can now be written as theta hat dot is equal to y when theta hat is in the interior. So right now I am not precisely mathematically writing down the expression for the interior of the set. I am just using int to denote interior. So when theta hat of t is in the interior, so how do we make sure that it's in the interior? We check for f of theta hat, and if it is less than 0, we know that theta hat is in the interior of the convex set. Of course, first we have to construct a convex set, but let's assume that we have constructed this set omega delta, and then the estimate theta hat is within this convex set, then we are fine. We just use the unmodified adaptive law. Then we look at the case where theta hat of t is at the boundary of this convex set, and the the dot product of y and del f is less than equal to 0. So, in that case y transpose gradient of f is less than equal to 0, which means that, as I mentioned, that y is either pointing tangential to the curve or it is pointing inside. So, in that case again we continue to use the same update law, else we modify the update law and we use the projection of y on the tangential plane, which is given by this vector tan, which we just found out. So, the expression for that is y minus del f transpose over del f square times y. So, we have actually taken out a vector, subtracted a vector which is multiple of y from y, and we get this modification which is which takes the component of y along the tangential direction, and that is the projection modification that we have to do. So, what is this else condition? This is the condition where theta hat of t is on the boundary of gamma delta and y transpose del f is less than 0. Okay. So, how do we now use that for the model reference adaptive control case? Let's look at that. Okay. So, projection based MRAC is what we will do now. So, we want to now see how this projection can be used in the model reference adaptive control, where we have some external disturbance. Okay. So, again let's consider for simplicity a scalar case, x dot equals a x plus b u, and we have a disturbance d. So, it is a bounded disturbance, and it's we want to follow the reference model a m x m plus b m r. The standard matching conditions are satisfied. So, although we consider a scalar case here, because we want to showcase the projection based modification and not complicate the analysis by considering a vector case, but you can trivially extend this to the case where you have A and B matrices. Okay. So, so for a direct MRAC, we design our U to be kx hat x plus kr hat r. Okay. Now, what I am going to do is a little different from what we have done so far. I am actually going to combine these two estimates into one. So, I will consider that we have x and r, and then I will combine these into one. Okay. And I call this as the regressor y, which is a function of x and r, and I call this as theta, which is the vector of unknown parameters, right. So, we this is given by y theta. So, y is 1 cross 2 and theta is 2 cross 1. Okay. So, u is a scalar. So, again y is a term which has known quantities, and theta is the unknown parameter vector which we need to estimate, right. In fact, this will be theta hat. So, let us make this theta hat, because an estimate of the actual parameter theta, which is so theta is given by kx and kr, right, which is the ideal values of kx and kr, which found out from the matching conditions if you know the unknown parameters a and b. Okay. So again, E dot is given by x dot minus xm dot, and we follow a similar procedure as before, and we end up with am e minus b. So what did we get previously? We got something like this, and plus a disturbance term. But now since we have combined kx hat and kr hat into this vector theta hat, we can do this a little differently, and what we'll get is minus b theta tilde, in fact y theta tilde, right. Okay, where theta tilde is defined as theta minus theta hat. Okay, so you can think of it as kx tilde and kr tilde, okay, plus d, which is a disturbance, right. So again, proceeding like we have done so many times in this course, we choose a Lyapunov function candidate to be some positive definite readily unbounded and decrescent function. So for this case, we conveniently choose it to be a sum of squares of the errors. Okay, so one thing I just want to mention is before we do the stability analysis is that we can easily show that the parameter here, the parameter estimate theta hat, will always stay within this bounded convex set as long as initially we start off inside the set. So using this modification, you can in fact go ahead and show that mathematically also you can actually show that once if you start inside, you will never be able to leave this set because of the modifications that we are doing. Okay. So our problem with parameter drift is solved if we follow these modifications. So it really works as far as removing the problem of parameter drift in presence of disturbances is concerned. The only thing that we have to show now is that this modification does not affect the stability analysis in an adverse way. Okay. Okay, so here gamma inverse of course is positive definite, and we assume that the sign of b is known. Okay, then we take the derivative of this. Now, the classical unmodified adaptive law for this case would be designed. Let's just go ahead and do the error system substitution. Yeah, we forgot the, yeah, that's fine. Minus theta tilde transpose gamma inverse theta hat dot, right. So if we choose theta hat dot to be gamma minus gamma y transpose E signum of B, then what we get is minus B E y tilde C D minus and signum of B and mod of B combine to give B, and then we can take the transpose of this term because it's a scalar, and then this cancels with this, and you're left with A m E square plus E d. And here, if you remember, what we did was we were able to show that if it was very similar to the dead zone case, where we were able to show that if the tracking error is larger than some threshold, then V dot will be less than equal to 0, which means that the tracking error and the parameter estimation errors are bounded. But once the tracking error becomes smaller than that threshold, that's where we are only able to show that the tracking error stays bounded, but the parameter estimation error can drift away and go unbounded, and that's where the problem started, and we started modifying our update laws and added robust elements to it. Okay, so here again we will have the same problem. We will only be able to show, so here we will, if you follow through with the analysis like we have done before, we will only be able to guarantee that E of t is bounded, but that's not enough, because we want to make sure that all signals in our system are bounded and the control is also bounded. So we can't guarantee that theta tilde of t is bounded, or kx tilde, kr tilde is bounded. And so we just mentioned that using a projection modification on our adaptive laws, we can ensure that the parameter estimates they stay bounded, but we need to show that such a modification does not affect our Lyapunov analysis. So remember, the Lyapunov analysis will have to change now, because we are not using this theta hat dot update law. We will not be using this at all times, right? It depends on where our derivative vector is. So if it is pointing outside the convex set, then of course we can't we will be using a modified version of this. Okay, so let's now modify this for the MRAC case. We've already done the basics required to construct a projection based law. So let's modify the update law using projection. So first, of course, we construct a convex set. That's the first requirement for this kind of a projection, where theta lies. So the actual parameter lies inside this convex set. So for that, as I mentioned, we have to assume that theta is less than equal to theta m, where theta m is a known constant. So that's very important, that this is a restrictive assumption in some ways, because we are saying that we know the upper bound on the adaptive parameters, which may not be available in many cases. Okay. So so how does this modification affect the stability analysis? That is what we want to see. Okay, so then we construct, we define a function f of theta as theta square minus, so we basically square both sides, and this is a convex function. So then we can, using this convex function, we can define a convex set like before. So here let's assume, let's just use delta, which is delta equal to 0. Okay, so this is the convex set where delta is equal to 0. Okay, and we use the modified update law now. So theta hat dot is equal to, so we represent it as proj. So this is the projection operator which projects theta hat to be within this convex set. So we write it as theta hat comma y, which is given as, so now we have the different cases. So we have theta hat dot equals y, which is derived from the Lyapunov analysis. So this is the case where your estimate lies within the convex set, which is f of theta hat less than 0, or if it lies on the boundary, then the dot product of y and the gradient evaluated at theta hat is less than equal to 0. So if this condition is true, then we use the unmodified adaptive law. In the case that this condition is not true, we have the else case where we modify this law like this. Okay, so this else is the case where y transpose gradient of del f theta hat is greater than 0, which means that the derivative vector y is actually pointing outside of the convex set. So in that case we want to project it back. Okay. So of course here we considered that initially at t equal to 0 we start within the convex set. So theta hat of 0 has to be less than equal to theta m, and we assume that theta m is known. Okay, so how does this modification affect the stability analysis? Okay, so let's go back to the Lyapunov function that we had considered, and I'll come to the expression for v dot, which was given by a m e square minus b e y theta tilde plus e d, and now we have plus theta tilde transpose gamma inverse, and we use proj of theta hat comma y. Yeah. So because so we'll have a negative sign here. Okay. So in case 1, so let's just denote these as case 1 and case 2. So this is case 1 and this is case 2. Okay, so for case 1, which is when theta hat of t lies in the interior of the convex set or on the boundary and pointing inside. The set. So, this is the case 1. So, in this case we know that projection of the projection operator will return the unmodified law. So, proj of theta comma y is equal to y, which is given by what we had derived last time, minus gamma y transpose E signum of B. So, if we use this as the update law, we will cancel this term in the Lyapunov derivative, and we will be left with V dot equals A m E square plus E d. So, this is the same situation that we had in the unmodified case. The difference here is that here we are making sure that theta hat is within the convex set. So, in this case we can say that both the tracking error and the parameter estimation error, they remain bounded. Okay. So, now let us talk about the more interesting case, which is case 2. That is the case where theta hat of t, it lies on the boundary of the set and is pointing outside the set. So, the derivative is pointing outside the convex set. So, that is the forbidden region that we want to prevent here. We want that it always stays within this convex set. We will have V dot as A m E square plus E d minus B e y theta tilde minus so there we will use the modified update law. So, this is I minus theta hat transpose norm of theta hat square times y. Okay. So, this I is in fact an identity matrix of dimension 2 cross 2. Okay. Okay. So, let us simplify this equation. So, we will have A m E square plus E d minus B e y theta tilde, and let us look at the first case, and so we will get a minus E theta tilde transpose gamma inverse y plus theta tilde transpose gamma inverse theta hat transpose. Okay. So, if you look at just this term here, let us try and simplify this. So, we will substitute for y, what we get is plus and this becomes B e theta tilde transpose y transpose, and then since this is a scalar, so you can take the transpose and nothing will change, get y theta tilde transpose. Okay. So, now this term in fact cancels with this term. and we will be left with AME square plus ED, and then we'll have this term to deal with. Okay. Okay, so let's manipulate this slightly. So of course the first two terms are familiar. We had obtained these terms in the unmodified case as well. We need to somehow make sure that this third term, which comes as a result of the projection modification, that is either negative or 0. So we would like that this term should be less than equal to 0, so that the stability is preserved. Okay. So okay, so now we break it down into two terms, this term and this term. Now if you look at the second term, which is this term, so this is case 2. So in case 2, if we go back, we see that for case 2 we had considered that y transpose gradient of f of theta hat is greater than 0. So what the function f that we had considered in this case is given by theta transpose theta minus theta m. So we take the gradient of f with respect to theta, and what we get is 2 theta. So this case 2 means that we are looking at y transpose theta being greater than 0. Okay. So we use this information here. So here this case is y transpose gradient of f of theta hat being greater than 0, which translates to y transpose theta hat being greater than 0. So this term is in fact greater than 0. Okay. So now let's look at the second term, which is this term. So if, I want to take you back to the lemma 2 that we had done in the previous class, where we had proved that so if you recall lemma 2, where we had proved that theta minus theta b transpose the gradient of f evaluated at theta b is less than equal to 0. So in this case theta b represents the theta at the boundary of the set, and case 2 in fact represents that the estimate lies on the boundary. So we can for case 2 we can write this as theta minus theta hat transpose, and the gradient at theta hat I have already calculated to be twice of theta hat. So we can just write this as theta hat less than equal to 0. So which means that we are looking at theta tilde transpose theta hat less than equal to 0. So can we use that information somehow here? Yes, we can, because gamma inverse is a positive definite matrix, and since theta tilde transpose theta hat is less than equal to 0, so this term is in fact less than equal to 0, since this is a positive term. So since this term is we have proved to be positive, and this term is less than equal to 0, so the combined term is less than equal to 0. So what we can say is that, let me rewrite this. So, this combined term is less than equal to 0, and this is V dot. So, we can further upper bound V dot by throwing away the term which is less than equal to 0. So, V dot then becomes less than equal to A m E square plus E d. Okay. So, we go back to the case that we had obtained for the unmodified situation, and in fact, here V dot is more negative than the previous case. So, the same conclusions hold, that we are able to guarantee, and with the so using this, of course we can guarantee that E of t remains bounded, and because we are using the projection which makes sure that the estimate lies within the convex set for all time, we also prove that theta hat of t remains bounded. So, in conclusion of this projection based modification, what we can say is that projection ensures that the parameter estimate stays within bounded convex set, and also that the stability is preserved even when a projection modification is used. So, we can say that using these 4 robust adaptive controllers, starting with dead zone and then sigma mod in E mod and projection, we have been able to robustify the existing adaptive controllers, so that they can work in presence of external disturbances, and we can ensure boundedness of all the signals in the system, which is extremely desirable for any control system. So, that takes us to the end of this 10-week course. So, in this course, of course, we have covered linear time invariant systems, but the idea was to expose you to the nitty-gritties of adaptive control design, and the same ideas can be extended to nonlinear systems as well. So, I hope that you enjoyed this course, and you were able to learn how to design adaptive controllers using Lyapunov based methods, which are not only analysis techniques, but also a design tool. Thank you so much.